Our next speaker is Jonathan Beebe, who has more than 40 years experience bringing the latest software design and data modeling technologies to the domain of lift control and monitoring. And Jonathan's paper is entitled Global Dispatcher Interface Initial Prototype Design.
Okay, I'm Jonathan Beebe. Thank you, Graham, for the introduction. I've got a lot to say and very little time to say it, so it's going to be a fairly brief, quick run through of the slides that I've prepared. And it's about a project that I've been undertaking for a few years now called the Global Dispatcher Interface. I'm trying to define that interface. I'm very enthusiastic about it, and I hope I can convey that enthusiasm to you in this presentation. I'm going to talk about. Oops, sorry. I'll talk about why I'm doing it, what the objective of the project is, what I hope to achieve. Then talk about the scope of this project and the methods I'm using to develop it. I'm going to talk about the requirements analysis and step through an example of a use case which covers the analysis stage of the project. And then I'll talk about how the results of that analysis are brought into the design stage. And finally, about a prototype, which I've implemented to prove that it actually works and that it's a good idea. So why a global dispatcher interface? Well, architects, building designers need to evaluate different control policies. Buildings are getting more and more complex, multiple entries, public spaces on different floors, private accommodation, residential accommodation, all in the same building. So designers who want to simulate the people flow through these buildings need to be able to simulate the effects of changing the control policy of a dispatcher, and ideally to be able to plug in different control policies to see whether that improves or otherwise affects the efficiency with which people flow through the system. They then need to move into the real world where the actual installation is, and they want confidence that they can transfer directly from the simulation exactly what they've simulated into the operational phase. So if they could unplug it from the dispatcher from the simulator and simply plug it into the lift motor room, then that would be ideal. Building managers and owners, sorry, I beg your pardon, want to monitor the performance and maybe adjust the configuration to cope with changes in the way that the building is being used. Increasingly, as quite a few of the presentations this morning have identified, we're seeing a much higher level of interconnectivity between the lifts and the services, the other services of a building, but also smart buildings and their relationship in the city in which they exist. There are many different types of devices now for registering landing calls for passengers to travel in the lift. You can do it through a personal portable device, a smartphone. There are room service robots in hotels that need to move from floor to floor, security access controls for the building itself, which directly link to the lift system. So there is a need for a standard interface to the dispatching capability. It's got to cover all types of lifts and groups, both now that exist now and in the foreseeable future. So we're talking about anything from a very simple duplex group to multiple cars, ropeless cars sharing the same lift shaft and moving independently up and down that shaft. It's directional calls, destination calls. So it really needs a sort of standard approach. So it's a large project. I'm conducting it independently in my spare time, and I've already spent 5 years on it. I think I've got quite a long way with it, but there's still a lot more to do. I've followed a formal lightweight systems development life cycle. That's based on use cases and the unified modeling language. I'll say a bit more about that on the next slide. And the results of this modeling are available on a public access website. So it's the project website, which I've published, and that consists of the model, which has text elements and also diagrams, and it can produce specification documents. Those are also on the project website. And at various key milestones in this project, I've published peer review papers through the Transport Systems in Buildings journal published by Northampton University, but also you can access it from the project website. So the first one in 2018 was the requirements analysis paper, which looks at how I approached identifying the users and their requirements. The second one, which was published earlier this year, covers how the analysis was taken into the design of an initial prototype to demonstrate its feasibility. And also, there's a key thing for me that it's independent of the technology that is used to implement it. So it's all about lifts and dispatching. It's not about which operating systems or programming languages or network protocols that I've used. And the obvious next step from that published paper was actually to implement this first prototype. The system development lifecycle is a recognized technique for developing software systems. It's a formal process, and its aim is to avoid missing things out, oversights, and also to future-proof the design. It starts off by identifying requirements for this global dispatcher interface. It takes initially a perspective from the user's point of view, develops passenger use cases, which are step-by-step descriptions of how the user would use this system. But it's not just limited to passenger use cases. It includes the maintenance teams, building owners, managers, etc. So you're building up a catalog of who's going to use the system and what they intend to use it for and how they will use it. And having done that, we then look at how from a systems perspective, how that system might deal with those requirements and deliver them to the users. So I developed a set of use cases for the dispatcher. And those use cases show how the different objects in the system interact with one another, and that identifies what objects are required and also how what roles they play and their responsibilities. And to do all this, you use a modeling tool. It develops this UML model. The UML stands for Unified Modeling Language, and that consists of these text elements, diagrams, and it can also produce reports, which is how I populated the project website. It's like a sort of very specialized word processor, this tool. So let's look quickly at one system use case, which is perhaps the most significant for a dispatcher interface, it's the assign call. And what you see along the top are the collaborating objects, and below there's a sequence of directed arrows which show how these objects interact with one another by sending messages to each other. We've got the objects along the top refer to things that you might recognize, like a landing call device or a car, but this is really just an abstract concept. It's not a piece of metal going up and down a shaft with electrical devices attached to it. It's just the concept, because we're still in an analysis phase. We haven't got anywhere near actually delivering a working system. So the use case, well, this is going to be a problem. Oh, right, okay, sorry. So it's initiated by the passenger making a request to travel to the landing call device. So that might be via a smartphone, or it might be a push button on the landing. The landing call device then sends a message to the dispatcher interface, and the message says that it's an event, it's a call registration, so a landing call has been created. And so I'd ask you to hold those three facts, or two facts actually. There's another fact I just remembered. It's currently, this landing call has no car assigned to it, because we don't know which car is going to answer that call. So if you could hold those three facts in your mind, I'll come back to them in a subsequent slide. There you go. So the dispatcher interface receives that message, and it invokes the dispatcher itself, which probably contains an algorithm which works out the best car to assign. But that goes on behind the dispatcher interface. There's another word I want you to hold on to. And so the dispatcher can be completely proprietary. We're not making any specification of how it works. All we know is that when it's finished, it will update, another word to hold on to, the landing call that's held in the dispatcher. Oh, sorry. The landing call that's held in the dispatcher interface with, in this case, the minimum cost car, the car to be assigned the call. So now the dispatcher interface has two jobs. It's got to notify two different objects that the call has been assigned. So that, another word, notify. First of all, it's got to notify the car itself, because otherwise the car doesn't know it's got to go and service the passenger's request. But it also needs to update the landing call device so that that device can confirm to the passenger, yeah, we're dealing with your call. And possibly if the destination floor is known, then to advise the passenger to go and stand in front of the assigned car entrance. So what can we learn from this analysis that I've just stepped through with this sequence diagram? And the answer is, it's all about information. Originally, when I started thinking about a global dispatcher interface, I thought, well, obviously there'll be a function call that says, assign this call. Actually, we never said that until we got right behind the interface to the dispatcher itself. We were talking about creating information, updating that information, and then notifying that information to somewhere else. But we do need a very firm, clear, controlled definition, agreed, open, and standard for that information. We need it to know its structure, how different bits of information relate to one another, all to do with the domain of lift control. And we need some rules as well of what values we can put into those pieces of information. And to do that, we fortunately have something called the Standard Elevator Information Schema, which defines all that. And this is a diagram of a landing call definition within that schema. The landing call is a complex piece of information. It belongs to a group which has a list of registered calls. And the landing call itself contains information like the time it was registered, the floor that it originated from, its direction, possible destination floor, but not necessarily, and the assigned, the car it's been assigned to. So when I mentioned before that initially that wasn't defined, but then the dispatcher did its job and it defined in an update the assigned to property, which is held there. Right, and in order to provide this in a standard way, we use something called a REST interface, and I won't tell you what that acronym stands for because I don't think it means very much. It doesn't help me, so I won't tell you. But it's it's infrastructure software, so it's provided by a number of third parties. You don't have to code it yourself. You don't have to maintain it yourself. Some of it is even available for free and open access, and you don't have to pay a license fee for it. And it has very simple functions that it offers, which are completely generic, nothing to do with lifts. There is a post, which is the equivalent of creating information. There's a put, which is equivalent to updating that piece of information, and a get, which is what happens when you read it back again. Oh, okay, right, okay. So the GDI, the global dispatcher is like a notice board. It contains the current state of information, and it's a component architecture. So it's that we've designed through this analysis. It's very flexible. What I showed you was the dispatcher sitting behind the interface, but in fact, it'd be equally possible for the dispatcher to sit in front of the interface and to use this RESTful interface in the same way as the landing call stations and the car does. Or also it could all sit behind the interface, in which case the interface just becomes accessible to applications like monitoring, data, performance monitoring, data logging, etc. Have I run out of time? This is the sort of block diagram of the prototype that I developed to do that. Fortunately, I had the use of Elevate simulator from Peter's research, so I can simulate all these different configurations of lifts and passengers, and I can use that. It has an API that I can drive software which creates the events, which are then sent to the global dispatcher interface. And in order to show that it's technology independent, the Elevate simulator runs on a Windows platform, my laptop, but the GDI actually runs on a Raspberry Pi, which has about as much computing power as your smartphone, and it has a different operating system. It's programmed in a different language. So I think that has proved that it is not dependent on some specific technology. And that's about it, I think. Yeah, so I'll just, have I run out of time?
A little bit over.
Okay, all right. Well, I won't say anything else except that security is really important.
Thanks.
Yeah, okay, thank you.